Alright, so this is my Physics of Superhero project, and I'm doing it on Wonder Woman. We can start with a little introduction of Wonder Woman. So, Wonder Woman is a superhero who is pictured in many generations of comic books. She possessed many powers over time, some dated back to the 1970s, when she had a blood transfusion from Superman. At that time, she was the wife of Superman and appeared in many of the DC comics. She met and fought along with many other superheroes such as Captain America and Batman. I can say that she's the good version of a less known superhero, Superwoman. Amongst the powerful abilities that she has, we can see that she has super strength, flight, and a golden lasso that could change her in any form she desired. On top of that, she has super speed, incredible reflexes, agility, and enhanced senses. Compared to Superman, she may have been pictured as weaker, but her speed, reflexes, and character put her at the same level. In modern times story, Wonder Woman is a descendant of the Amazons living in Atlantis, but forced to come to the normal world to defend it. And we can go with the first unit, which is kinematics, and this is part of the momentum and energy paragraph, but is explained here for kinematic parameters. So with respect to speed, acceleration, and distance. We can assume the following: that somebody is shooting a bullet at Wonder Woman from a distance of 30 meters away. In order to block the bullet, Wonder Woman will have to move her hand 1 meter up, and that will be done by accelerating for half the distance and then decelerating for half the distance. And we know that the muzzle speed of the bullet is 380 meters per second. So then we can use a formula which is time is equal to distance over velocity. So then if we put our values in, we'll get a time of 0.078 seconds. And that means that Wonder Woman will need to move her arm for 1 meter in 0.078 seconds. We will assume that she accelerates her arm for half the time and then decelerates her hand for half the time, so when she blocks the bullet, her arm is not moving. We will have the following data to work with. Wonder Woman's arm accelerates constantly for 0.039 seconds over a distance of 0.5 meters. Wonder Woman's arms decelerate constantly for 0.039 seconds over a distance of 0.5 meters. And we know that Wonder Woman's arm weight is 4 kilograms. So then if we use a distance formula, which goes distance is equal to acceleration times time to the power of 2 divided by 2, and from here we can simplify it to acceleration is 2 times the distance divided by time to the power of 2, and if we plug all our values in, we'll get 657.4 meters per second squared as the acceleration. When she slows down her hand, she'll have a negative acceleration of 657.4 meters per second squared. The speed of her hand, which when it reaches midpoint, is velocity max is equal to acceleration times time, which would be 657.4 meters per second squared times 0.039 seconds. So then our max velocity would be 25.6 meters per second. And then we can go into the second unit, which is kinetics. It goes as is. In one of the episodes, Wonder Woman has a shield which can block various threats, including a bullet. In this scenario, a certain gun is being fired at the shield where Wonder Woman has to block it. The gun, the Gewehr 98, has the capability of firing at a velocity of 850 to 950 meters per second, and a travel time of about 1.524 of a second. We know how much the bullet weighs in grams, which is 9.9 grams. Using all this information, we are able to identify the force at which the bullet impacts the shield at. Newton's second law says that the net force is equal to the mass times acceleration, so F net is equal to ma. Since we do not know the acceleration but velocity and time, we can substitute what we know for acceleration. Acceleration can also be written as velocity over time. Plugging that in for our acceleration, we have all known variables to work with and are able to find the force at which the bullet strikes the shield. We can relate this scenario also with Newton's third law, where every action force has a reaction force. If the bullet hits at a certain force, then the same exact force will be hit in the opposite direction, meaning back at the bullet. And then here we have our equation breakdown, so F net is equal to ma, and we know that acceleration is equal to velocity over time, and then we have our mass and our velocity and our time. So instead of writing F net is equal to ma, we can substitute the a for velocity over time, and then it turns out that our net force is 144.963 newtons. We can go to our third unit analysis, which is momentum and energy. Regarding the situation with the bullet hitting the bracelets, we can see that momentum comes into place. We are able to use the momentum law between the bracelet and the bullet to find the momentum before the collision and the momentum after the collision. There is one main rule here. In every collision, the momentum before is the same after the collision, meaning all momentum is conserved. In the collision, we are able to analyze that we have a moving object, which is a bullet, and a stationary object, which is the bracelet. We know that the bullet initially is moving and will still be moving in the opposite direction after the collision. A bullet is fired at Wonder Woman, and it bounces straight off her bracelets. We are applying the law of momentum conservation, which is total momentum before the impact is equal to the total momentum after the impact. Before the impact, the only thing moving was the bullet, and Wonder Woman was stationary. After the impact, the bullet deflects at the same speed, and Wonder Woman is pushed back a bit. Momentum is mass times the change in velocity, and the velocity of the bullet is high, but the mass is really low. That means the bullets actually don't have that much momentum. They don't really knock you back that much, even if you're wearing an armor or vest. So here we know that momentum is mass times velocity, and then we have our initial momentum is equal to our final momentum. And then we did our momentum law, and after that we found that the velocity afterwards was 0.008 meters per second. The velocity of Wonder Woman after that bullet strikes her bracelet, so she does not really move back at all. And we have some assumptions here. So the mass of a 9mm bullet is 7.5 grams, which is 0.0075 kilograms. The muzzle speed of a bullet, which is 380 meters per second. And the mass of Wonder Woman, which is 60 kilograms. Plugging all the data into the equation, we obtain the speed of Wonder Woman after the collision as being 0.008 meters per second, meaning she will not move back much and will be able to deflect the bullet. Going back to this slide again, we're just going to briefly go over it as we're going to be using these values, like our time and our acceleration, for energy and for force. When she moves her hand, there's an increase in kinetic energy from 0 to our kinetic energy formula, which would be mass times the velocity squared divided by 2. And then we see here, if we plug our values in for our kinetic energy, we land with 1,311 joules. It will take the same amount of energy to stop, so the variation of kinetic energy is actually 2 times the kinetic energy. So if we multiply our kinetic energy that we found above by 2, we would get 2,622 joules. And then we would go to the power required to execute the blocking move. And we know that the equation for power is equal to energy over time. So if we take our energy, our total energy, which is 2,622 joules, and we divide it by our time, which is 0.078 seconds, we come out to a power of around 33,615 watts. And then we can also go into force. So the force required for Wonder Woman to lift her arm is as follows. We can see that our force is equal to mass times acceleration. So then if we know our mass and we know our acceleration, so we can find our force. So we multiply 4 kilograms by 657.4 meters per second squared, and we come out with a force of 2,629 newtons. As talked previously, we're going to be going into a different unit, which is fields. And we know that, we already talked about it, that Wonder Woman has the ability to fly, and that means anywhere she'd like to go, she can make it happen. By having this ability, she's able to fly around the earth and look down and identify villains that want to do nefarious things. I will assume that she is circling the Earth at an altitude of 2 kilometers, and I will find the speed required to make that possible in the Earth's gravitational field. The orbit speed is calculated with relation to circular motion. We know that an object in circular motion exhibits centripetal force. If we equal both equations, centripetal force and gravitational force, and rearrange for v, then this is our orbit speed in which Wonder Woman orbits around that planet. And here are the values that we have. We have the gravitational constant, we have the mass of the Earth, we have the radius of the Earth, and we have the radius at which she orbits, which is 2,000 meters or 2-kilometer altitude. So when we equal our centripetal force to our gravitational force, we get mv squared over our radius and gmm squared over our radius squared. And then after that, our equation that we get for velocity is the root of gme over divided by our radius. And then plugging everything in here, we can see that our velocity would be 7,905.7 meters per second. And with this, we can then conclude that Wonder Woman's speed in a 2-kilometer circular orbit is 7,905 kilometers per second. And then here is the works cited, which is in APA format and in alphabetical order.